Now that we know what I is, we can start doing some math work with it. And the coolest way to think about it is just as a variable itself that has one unique identity. And you'll see how that works in a moment. So in a straightforward sort of collection of like terms, you collect like terms just as you normally would. 7 and 2 are both real numbers, which means that 7 minus 2 would give us 5 for the real component. And then 3i plus 9i, those are the imaginary numbers. Well, 3 plus 9 is 12, so this just becomes 5 plus 12i. Pretty straightforward. Once we get to multiplication, this is where the tricky part comes in. 2 times 3 is 6, and I times I is I squared. So in the same way that if this were 2x times 3x, we'd get 6x squared. The variables operate in the exact same way. The one difference is that I squared has an identity. We learned this in the last video. I squared is equal to -1, which means that 6i squared can actually be further reduced to 6 times -1, which means that the answer to this problem is actually -6. So an imaginary number times another imaginary number suddenly becomes real again. And this is what Raphael Bombelli was so excited about, because he could take something, venture into numbers that did not exist, and eventually emerge back out on the other side with real answers again. So, in a more complicated form, if you were doing binomials, well, this just works the same way that any other multiplication of two binomials would, with the one addition of this process. Anytime you have an I squared, it's going to turn into a -1. So, foiling first outside, inside last, or if you wanted to set up a box method, you can, but here, 1 times 3 is 3, and 1 times -4 is -4i, and 2i times 3 becomes 6i, and 2i times -4i becomes -8i squared. So there are like terms, and then there's that identity we're going to use. The like terms, -4i plus 6i, becomes 2i. That 3 is unchanged out front. And then minus 8 times, well, I squared is -1. This can be then multiplied out, so -8 times a -1 is a positive 8. So I have 3 minus 2i plus 8. But then I have two real numbers again, and so I can further compose those down. 3 plus 8 is 11, and then the minus 2i gives us another complex number. So a complex number with a real and imaginary component times another complex number with a real and imaginary component will end up giving us another complex number with a real and imaginary component. Pretty cool.